Yeah, similarly, I will continue with the microalgae biomass to biochar. In this study, because in the previous study, we found that our focus is on the biochar. Then we found that the reducing sugar, the sugar content is produced. So in this study, we also convert that reducing sugar to bioethanol. At the same time, also the biochar that we obtain and we produce, and we do the further analysis. We found that it might be suitable for the bioabsorbent. We also conduct the bioabsorbent study. So let us start this study. The instruction, I'm not going to go through the microalgae. I think all of you already know. The microalgae is able to fix the CO2 with the help of the sunlight. That one. Very good. Then this one is between. Again, we are using the vector vector. Vector vectors. This is the comparison between the pyrolysis and also the vector vectors. Then this is the potential application of the biochar. It's almost similar. Can be used as the bioabsorbent and also the solid fuels, and also for the carbon sequestration and as well as the soil amendment. This one is the same thing. So we focus on the third generation of the microalgae to produce the bioethanol. Okay, the aim. The aim of this study is to investigate the simultaneous production of the biochar and hydrolysis byproducts from the microalgae, the chlorella, using the wet conversion with microwave assisted acid hydrolysis. And it's the first part. And the second part is how we going to convert the microalgae bioethanol production from the acid restricted hydrolysis product from the first study. And the last one objective is to utilize the microalgae biochar as the bioabsorbent for the dye pollutant for wastewater treatment. Similarly, similar process, we are using the wet microalgae biomass with the household modified microwave acid heating factors. Then we have two products. One is the solid biochar, another one is the liquid hydrolysis product. For the liquid hydrolysis product, we further analyze for the total reducing sugars concentration. Then we found that it has the sufficient amount of the reducing sugar which enable us to convert into the bioethanol. And similarly for the biochar, we go to the possible and ultimate analysis, the HHV, TGA, FPL, and SCM analysis, and see what is the potential applications. And in this study, we further analyze the bioabsorbent capability of the biochar that we produce. This is household modified with the temperature 160 to 170, 5 to 10 minutes. Just using one type of the acid, which is the sulfuric acid. Pressure maintained at 2.5 bar with energy input only 10 ampere. Yeah, this is the amount. The 20 gram of the microalgae with dilute with the 100 ml of the dilute sulfuric acid. Yeah, this is the amount that we are using. Just now, someone asked what is the amount that we are using. And this is for the fermentation process. This time we are just using the 50 ml of the microalgae hydrolysis solutions mixed with the yeast, the nutrient that we are using, the yeast, and also some nutrients for the yeast, which adjusted to pH around 4.6, suitable for the yeast to survive. So this is the inoculum yeast that we are using, 1.5 gram per liter. Then first with nitrogen before the fermentation process. Then we control the environment at 29 degrees C with the non-aggregation stage using the dark fermentation. We are using the dark fermentation for this fermentation process. So this is the preparations for the absorbent study of the biochar on the dipollutant uptake. So two types of the dye that we are using. One is the methylene blue, and the methylene blue and the conglomerate. This most common pollutant happen in the wastewater. And to determine, we determine the final absorbent using the UV with the wavelength between the 665 and 497 nanometers for the methylene blue and conglomerate respectively. So this is the method that we use to analyze the solvent capabilities. So this is the preparation, the UV, microcentrifuge. This one is the thermocycle. So this is the calculations that we are using to analyze the biochar and also the percentage of the removal and also the absorbent capacity. So what is the maximum absorbent capacity that can take for the biochar? Then at the same time for the biochar, we analyze the SEM, see the pore size, pore size, the porosities, and also the what is the surface areas. And also the pH analysis to see whether what is the pH and also what is the charge for our biochar. So the effect of the absorption factor that we analyze is the pH. Whether the pH will affect the absorbent capacity or not, and also the bioabsorbent dosage and the initial concentration and also the contact time. What is the total contact time in order for the biochar to absorb the maximum capacities of the dipollutant. So we also adopt the isotope model fitting to find the equivalent absorbent study to see the bioabsorbent capabilities. This is the three models that we are choosing. See which model can be fulfilled, in line with our study. Okay, now go to the discussion. The first part of discussion is almost similar, but this time we are using a slightly different species. Still, the first species still using the Correda ESP31, and another one is the Correda GP. This is also another genetic modified species which rich in the proteins. Then we found that for the previous study, we found that if the microalgae rich in the carbohydrate content, it has the advantage in the bioethanol production. So we have this hypothesis. So that's why we conduct this analysis. So after the wet correction, we found that this is a similar, almost similar result that we obtained from the previous study, with the increase of the acid concentration, the total biochar here is reducing, of course, reducing with the different conditions, with all these conditions, the biochar here will be reduced. Similarly, for these two species, the only difference is the degradation of the protein-rich microalgae is lower compared to the Correda ESP31, which is rich in the carbohydrate. At the same time, in this study, we analyzed the total reducing sugar. We found that the total reducing sugar is increasing. It's increasing. Why? Because the previous study we showed that the top rate is if we go through the wet corrections under the hydrolysis, the acid hydrolysis process, the carbohydrate content will be converted into the using sugar, using the glucose. Using sugar, there are many glucose, so there are few compounds. So the total reducing sugar will be increased with the increase of the acid concentration. Yeah, this is in line with what we have. This is from the previous study. Similarly, for these two species, but the only difference is what you see. The total reducing sugars for the carbohydrate rich
100 grams.
yeah, is around 100 grams. This one is around 20 grams only. Which is this one is 5 times higher. 5 times higher. But we can make one hypothesis what? With the highest total reducing sugars, the total amount of the bioethanol can be converted is higher. Right now. So this one we can convert into the bioethanol. While at the same time, we also look at the biochar. The biochar. Generally, the biochar, the heating values, the heating values for the biochar is increasing with the increase of the acid concentration for both species. But we can found that the carbohydrate rich microalgae the increasement of the HHV is highest compared to the another species the Corella GP. This one only 23 increased to 22 increased to 23 only very small percentage. But while another species is increased close to 50%. 50%. Better for few properties. Then this one is for the energy yield. The energy yield is reducing for both species also same. Reduce with the total acid concentration increase. This one nothing much. Yeah, this one might be suitable for the solid fuel. So this one is what derived from for the TGA on the raw biomass and biochar. The waste loss occur between the 100 to 300 degrees C is due to the what? Decomposition of the carbohydrate and also the protein. This one here. Here, the peak is come from here. So this is the SEM analysis. So because you see this one is the before back correction, this one after back correction. We can see the porous is increased. This one is how many times? I forgot already. This one still also. It's up to the 50 micron. I don't know how many times already. It's not significant, right? You see, you can see the porosity is increased very clearly increased. So yeah, so this is what we found. The outcome is almost similar with what we found from the previous study. The co-production of the microalgae biochar and also the sugar can be recovered for further bioethanol production by using the microwave assisted production from the microalgae biomass. Then the Corella ESP 31 have the high total reducing sugar which up to 98 grams per liter compared to another species. However, another species have the high biochar yield up to 74%. 74% compared to Corella ESP. Then the microalgae biochar after back correction, the HHV is increased potential for the alternative solid fuel. Then the porosity structure. So make them it's interesting to further study about the bioabsorbent. See whether it really can absorb some pollutant or not. This one. So, but one interesting finding is what? Similarly, from the previous study, we also found that the 5HSN that we produced right now for the pathway that I show you, the 5HSN that we produced in the hydrolysis after the wet reaction process. The 5HSN, the amount of the 5HSN also increased with the increase of the acid concentration, which we found that Chlorella ESP has also higher amount of the 5HSN compared to the species, the Chlorella GD species, which is protein rich microalgae. So this one and reducing sugar, this is produced as a byproduct. The higher solubility of the acid, the greater degradation of the sugar into the formation of the 5HN. So sometimes, as I mentioned yesterday and the day before, the highest value not necessarily the optimum result. And you want to focus on what is your product, because like in this study, we found that yes, if we increasing the acid concentration, the reducing sugar might be increased. Right now, it's good for you to convert into the bioethanol, but at the same time, the 5HSN will be produced. 5HSN also one of the very good compound for the chemicals processing industry. However, later on I will show you what is the negative impact on the bioethanol production. You see, as we expected, if the highest reducing sugar it produce the highest bioethanol or ethanol concentration will be increased, right? Correct not? But it is not, because for this one, you see, for this one, why? Because it the fermentation condition is unfavorable for the bioethanol. Why? Because we have the 5HMS. The 5HMS is the toxic inhibitor, for the yeast. So make the fermentation process fail. Understand not? So that's why, because the amount of the 5HNF is already reached the maximum tolerance limit of the yeast or for your fermentation condition. So that's why the ethanol concentration at this point or these 2 points are lower. So the highest value is not necessarily the optimal value. So we need to see what is the optimal value of the product that you want to obtain. That's the thing. So this is the discussions. So the ESP is potential candidate for bioethanol. So the bioethanol can be obtained is 7%. 7% is a very good amount if consider this is a byproduct and we want to obtain from it. However, the 5HMF can be the toxic inhibitor for the fermentation process. But this compound is very useful in the biofuel. It's very useful in the biofuel conversion as a fuel additive or as a polymer or resin for the prosecutions in any chemical process. So, in the future, we might be considered to extract or to separate up the 5HMS before go to the fermentation process. So this is what we learned from this study. Then another second part is what? This is the SEM study with 500 times. This one is 500 times. We found that they are the biochar produced. They have the microporous material, which is the pore diameter is less than 2 nanometers. Then the BET surface area is around 2.65 meter square per gram, which make them is suitable to be used as a bioabsorbent. Yep. So that's why. Then we conduct the PZC test. The PZC test, we found that the biochar that produced has the pH 3.7. If the pH more than 3.7, it has the negative charge. Has the negative charge. That means what? If the pH more than 3.7, it can attract the cationic dial, which is the methylene group, cationic dial, methylene group. If the pH less than 3.7, it has the positive charge for biochar, which is suitable for the anionic dye, which is favorite for the conglomerate, for red color. This one methylene blue color. This one is not. So this one is we just do the see the initial pH, initial pH. So this one also we study, we also study the effect, one by one, effect, see what is the correlation between this effect. The first effect we study is about the pH, with the initial condition with around 50 ppm. The absorbent dosage is about 5 grams per liter, with the agitation rate of 150 rpm and temperature 30 degrees, which is the room temperature with the equivalent time 120 hours for methylene brew and 24 hours for the conglomerate. So we found that the removal percentage for both for both dye can reach more than 90% easily, no matter what is the pH, what is the pH. Then we want to see what is the effect of the absorbent dosage, the initial dosage, which we found that for this one methylene brew, for the methylene brew, the absorbent dosage is 1 gram per liter, which it can reach up to 85% already. The removal can reach up to 85%. Which remove around nearly 40 milligram per gram of the methylene group pollutants. While for the conglomerate, it can reach up to 95%, which equivalent to the 23.77 milligram per gram of the conglomerate dye at 2 grams dosage, 2 grams per liter, the dosage. This is what we found. However, the effective contact time is increasing. It's increasing from time to time. It's increasing. The removal of the methylene group, which is optimum percentage at around 120 hours, with more than 80%. Then this one is in minutes, but for the conglomerate, after 4 hours, it almost can reach up to the 100% for the 10 ppm. Then more than 80% for other ppm. So the optimum contact time or the optimal effective contact time is around 4 hours. 4 hours if you want to remove the conglomerate color. So this one is what is the model that track the absorbent capacity that we are following. So for this study, we use 3 isotherms. One is the long mill. This one, these two, another two. Tanking also, so see which one is closer curve to our absorbent capacity. So this is our experiment data, and we got the graph, and we found that the Ramil isotope model is closer. Both I can say all is almost similar, but the Romeo is isotope is assumed to be the closer to our biochar absorbent, so it can follow the Romeo equations. So from here, we found that what the microalgae biochar is the microporous absorbent with the diameter 4 diameter 0.665 and the optimal absorbent for the both dye, methylene blue or the conglomerate is at pH. So we don't need to modify the pH of the biochar. So for the dosage is 1 gram and 2 grams per liter for the methylene blue and conglomerate respectively. And effective contact hour is 120 hours and 4 hours for the conglomerate. And the maximum absorbent capacity is 113 per gram, and also 64 milligrams. So the long meal powder, so the best fit absorption with monolayer for our So this is the short conclusion. I mean, from this study, we found that after the wet surfactants, liquid product are able to be at the same time get our biochar, which is suitable. Is one of the bioabsorbent for the treatment. So this is extended from the real study. Yep.
So, more features.